results. What we did so far is that if your manifold is open, then we showed that the symplectic, okay, loosely speaking, symplectic forms in a given cohomology class, they satisfy H principle. In fact, in particular, we showed that every almost complex manifold is a symplectic manifold. In fact, you can choose the symplectic form whose associated compatible almost complex structure would be homotopic to the almost complex structure that you started with. And the second one is that these contact forms satisfy principle. So these are the results on open manifolds, and we saw that this can be deduced from Gromov's theorem on H principle. So today in the morning, it has been mentioned that twisted contact structures this is on any manifold, closed manifold, satisfy the parametric H principle. This is a result. This complete classification is by Eliashberg, but earlier, possibly the first H principle observation was due to Lutz. But recently, this was initially for contact structures on 3 manifolds, closed 3 manifolds. And then recently, this has been extended to, the notion of over-twistedness has been extended to arbitrary odd dimensional contact structures, and it has been shown that over-twisted contact structures on satisfy H principle. On the other hand, if you are working on closed symplectic manifold, we saw that the example of S6, which is an almost complex manifold, it's a closed manifold, but it doesn't admit any symplectic form, because if it has to admit a symplectic form, then it has to be exact. But this is an option. If you just cannot admit any exact symplectic form because of Stokes' theorem. But supposing that, in fact, what we know is that no closed, no closed manifold can admit an exact symplectic form. But supposing the cohomology condition is satisfied, the result is due to Toms. He proved that even if the cohomology condition is satisfied, that means, see, if there is a omega, is a symplectic form, then omega to the power n becomes a volume form, and so naturally these powers has to be non-zero because of the similar reason. So Toms showed that if you consider CP2 and take its connected sum, this space will admit an almost complex structure, but does not, also these conditions will be satisfied. So there is a cohomology class which is in the H2 whose square is non-zero, so but does not admit any symplectic form, though the cohomology conditions are satisfied. So in the symplectic case, there are a lot of open things and which cannot be answered in terms of H-principle type results. Now, we shall now consider some more H-principle type results, basically from coming from isocontact immersions, isosymplectic immersions, then Lagrangians, immersions, and similarly Legendrian immersions. So let me first define, already these things have been defined. So a map F, suppose you are in a contact manifold, and so this is n to n plus 1. If it is an immersion such that this F star alpha, this is 0, this is already mentioned. Now suppose you have two, okay, let's contact manifolds. So these are the two contact manifolds. A smooth map, which is an immersion, is called isocontact if the following are satisfied. First of all, it has to take the xi inside eta, in fact something more. So you can write it as df inverse of eta, this is equal to xi. So this can be expressed as follows as well. The derivative map f will take xi inside eta as well as f will be transverse to this, then that condition is satisfied. And the second is df is taking xi into eta. Here I have a, I denote this by d prime alpha, meaning that it is the restriction of d alpha on xi, and here this is d prime lambda. Now these are symplectic forms by the definition of contact manifold, and df is conformal symplectic. That means df will pull back d prime lambda onto some multiple of d prime alpha. Because generally this is not uniquely defined, this alpha and lambda. So this is a definition for the isocontact immersion if conditions are satisfied. Now if you look at this definition, the result says that, okay, the H principle says that this contact immersions, they do satisfy H principle. But if you look at the defining relations, these are closed relations. And there is no restriction on the domain manifold. It may be closed as well as open. Of course, I will need some restriction on the dimension. I'll come to that later. Now, how to use Gromov's theorem to prove these results? The first observation is the following, that there is, this theorem says that isocontact immersions satisfy H principle. In fact, parametric H principle, but let us not go into all these details. So isocontact immersions satisfy H principle. First of all, I have to express them in terms of certain differential relations. So our jets should satisfy this condition, right? This is at fx and this is xi x and dfx from xi x to eta fx. This is conformal symplectic. So this is the equation. But these are basically equalities. So far we have been working with open relations, whereas these are closed relations. So these are defined, these conditions defines a closed relation in the one jet space of one forms. That means this, if you consider T star M, it's one jet space. Here, this will define a subset R here. So that is characterized by the state equations. Also, you have to assume that dfx is injective. So these are the three conditions, 1, 2, and 3. Except from this one, this is an open condition, but these two are closed. So doesn't, Gromov's theorem doesn't apply to this directly. But so far we have seen many results, the contact case, which is very much topological. For example, you have Darboux theorem, which says that if you have a contact form, then any contact form locally will look like the contact form. So this is one result that, so let us recall some of the results from contact topology. So by Darboux's theorem, so every contact form locally look like standard contact on R3. And also there is another result which was mentioned. So this is Gray's stability theorem. It says if you have on a manifold xi t, so these are contact structures on some manifold M, and this is a smooth family of contact structures, then there exists an isotopy, let's denote it by delta t, such that this delta t is so delta t pulls back the or push forwards the contact structure xi naught onto xi t. So these are the stability theorem that will come to our help. So now, if we recall how we are going to approach this, the proof. So in the initial case, so in the Gromov's theorem, your R was open and deep invariant. So how the openness was useful? Openness that implies two things. One is, if you have an infinitesimal solution to R, that means if you have an alpha, which is, let's write x, y, okay, so some jet, x, y, alpha, if it is in R, so and f is its representative, then automatically, because R was open, it shows that f, whichever representative I choose, f is locally a solution of R. That was immediate. But here, in this situation, suppose you have an isocontact immersion, that means you take a jet of an isocontact immersion, so f star lambda would be alpha or some multiple of alpha, certain point x. Because of this condition, suppose I choose a jet which is here, so let us write it C, in RC. So fj1 fx belonging to RC, that will mean that f star lambda will be some multiple of alpha at that point. That doesn't mean that f star lambda will be a multiple of some multiple of alpha near a neighborhood of this. But what we can say is that this f star lambda is a contact form, because at x it satisfies the contact condition, and contact condition meaning, I mean that contact condition means alpha wedge d alpha to the power n not equal to 0. So whatever this form be, because it has satisfies the contact condition at one point, it has to satisfy the contact condition on a small neighborhood of that. So f star lambda is a contact form but may not be alpha. But this is equal to, so this is a contact form and it is some multiple of alpha at x. Now one can use Darboux theorem to show that you can get an isotopy delta t so that the final map will pull back f star lambda to some multiple of alpha. So Darboux theorem implies that there exists an isotopy delta t such that delta 1 star f star lambda would be some multiple, maybe not be the same, in alpha. So basically, when I'm be solving the local thing, and so this would be my, so f compose delta 1, I will replace this f by my f composed delta 1. So at each point x, if I have an infinitesimal solution, I can replace the representative f that I had chosen by some other representative which is coming from the Darboux theorem. Okay? Now this process has to be continuous. Initially we said that if we have a continuous section of R, so this is suppose, so sigma x will belong to this fiber over x. I can choose a representative of sigma x continuously with x using some Taylor's argument. So instead, if I have some section sigma, for each point Rx, I will get a representative, say Px, which is isocontact on some neighborhood of x. So here this Darboux theorem comes into help. So actually your sigma x, if you take an arbitrary representative that may not be isocontact, but using Darboux theorem that representative to get an isocontact thing. So the thing was that if you recall the picture, I was explaining everything in one dimension, so your space n was R2 there, but here, and this is some subset. If you have a point, around each point I was getting a neighborhood on which you have a local solution. And then we we used some interpolation argument to define a solution on a neighborhood of this set interpolating between these two solutions. So that was the idea. Now, here also you have, so the first step is done because of this fact that every infinitesimal solution can be okay, I can choose a representative such that I can choose these representatives continuously. So that was the first, choosing local representatives. That was the step one. The second step was this interpolation. So you have a solution, local solution here, you have a local solution on an overlapping patch, how to interpolate between these two, okay? And there we said that because of R, we have certain property on the solution space which is called the microflexibility. So if you have a pair of compact sets, and suppose you are considering solutions of R over B and look at the restriction map, solutions of R over A, so you have a restriction map here. This map, because R was open, this map turned out to be a microfibration. Microfibration means if you have a covering homotopy problem, you can lift the initial part of the homotopy. Now, that follows almost immediately because R was open, and that microfibration property was used to prove that there exists such an interpolation. If you have local solution here, you have local solution here, you can get a solution on some neighborhood like this. Now, this step 2 will be following, will follow here in this case. Of course, that is not immediate. Here the argument was this. So if you can somehow extend, because solution R over B, that is sitting inside some C infinity functions on open B. Now somehow if you just get one lift of this is a homotopy, say, I just ignore the P, so you have some covering homotopy problem. Here actually you have something inside solution of R over A, which is sitting inside C infinity open A. You can anyway like this. Suppose this is an arbitrary lifting. Now because of R, because initially you are already inside the solution space for time t is equal to 0, it follows that for small time t less than epsilon, your lift will lie inside the solution space because of the openness of Rn. But here again the R is not open, but we have Gray's stability theorem. So suppose you have a homotopy of isocontact immersions on the base, and the initial thing you can lift it to an isocontact immersion over B. Here I am assuming B is bigger than A, I think. Sorry, it's in. Anyway. Yeah. So I can start with some immersions. So they are in particular isocontact, where the initial map can be lifted over B, and that is an isocontact. But from Gromov's theorem it follows, or actually Smailhurst theorem, that if you restrict to the immersions over B and restrict it to immersions over A, that is a microfibration. So you can have a lift at least to the immersion space. So in particular, you can lift this homotopy to immersions defined over open B. Now I am claiming that your dimension of M is equal to dimension of N. If dimension of M is equal to dimension of N, these are immersions, So when you are looking at any map, whatever this is, suppose this is f tilde, so this is f tilde at time t, if you look at the star, this would be contact for small t. Why? Because f0 tilde star lambda, that was a contact already. And these B and A are compact pairs. So f0 tilde is a contact thing and contact condition is open. So for small values of t, this will also be a contact form. This is why I have assumed that this. Now once I have got a continuous family of contact structures, I apply again the stability theorem by Gray and form this with some isotopy to a, okay, here will be further, I can pull it back, delta t, which will pull it back to xi 0. So there are two steps things. First, I take a lifting of this into the space of immersions so that these are pulling back lambda to contact structures, but those contact structures need not be equal to the initial contact structure xi 0, which is xi. But then I apply further one diffeotopy given by Gray's theorem so that I can pull it back to xi. So the composition of this ft tilde together with delta t will give me an isocontact immersions. So this proves that here, if you replace this by RC as well, that means the relation corresponding to the isocontact immersions, this becomes a microfibration. If you have a homotopy here where the initial map of the homotopy has a lift to this, then a small part of the homotopy, initial homotopy, can be lifted here. So this is the basis of the interpolation that we did in this part. That is also resolved. But here in the process, as you can see, I assume that the two spaces have the same dimension. That is an extra assumption that I took. Okay? So in general, when I stated this theorem, here m must be less than n. Okay? So how to resolve this issue? Okay, another thing, okay, we are starting from some m, this is xi, which is kernel of alpha, and okay, so you have Tm, so you have a formal solution. So this is a formal solution. That means F is a monomorphism which satisfies this condition, and F is conformal symplectic. That means it pulls back the symplectic structure onto some multiple of symplectic structure here. Now using this formal solution, we can embed the manifold M into another manifold, which will denote by M tilde, whose dimension is same as the dimension of N. Okay? So I will have a manifold M tilde, and not only that, there exists with a contact form alpha tilde that restricts to alpha. Okay, may not be exactly alpha, but some multiple. So this is the situation. So I have M alpha, and it can be embedded inside another manifold M tilde alpha tilde. such that this pulls back alpha tilde onto alpha. So how does one do this? So basically here, because capital F is a conformal symplectic, it maps your xi as a symplectic subspace inside your Tn. One looks at basically, so if you have the, okay, if this is covering some map F, then one looks at F star Tn and then, F star xi star eta. So eta is a subbundle here. So one pulls back F star eta. F xi is contained in eta by the you quotient xi by identifying xi with capital F xi. So this turned out to be a symplectic vector bundle because xi is a symplectic vector bundle. This is a symplectic vector bundle. So this is a subbundle. So you take the symplectic complement. So that has a symplectic structure. So this is a symplectic vector bundle over M. And now if you look at the dimension, this exactly matches with the dimension of capital N. The total space dimension of the, let's write it E, dimension of the total space E is equal to dimension of N. So here you have a symplectic vector bundle which is sitting over a contact manifold. And then that data is sufficient to conclude that there will be a contact form on the some neighborhood of the zero section here. So M is sitting inside E on some neighborhood, at least you can get a one form alpha tilde that pulls back to alpha on M and whose restriction to each of the fiber will be given by the fiber property. So that is how one can, so starting with this formal solution data, you can embed your manifold inside this. So instead of considering isocontact immersions at the level of M alpha to N lambda, we consider the problem here with respect to M tilde alpha tilde. Okay, let's write it differently. Xi tilde is alpha tilde. So instead, you look at the problem here. Now here you have the equidimensional situation, and this formal data can be extended as well as to this situation. So now, whatever I have done before applies to this situation. So if you have a formal isocontact map, then you can homotop that map to a genuine isocontact map. And because of this fact, so you have got an isocontact map on a neighborhood. So this H principle, so Gromov's theorem, some modification of Gromov's theorem would imply that there exists an isocontact map on open neighborhood of M in M tilde to N. And now, because of this fact that the restriction of alpha tilde to M is alpha, if you restrict this solution, this isocontact map to M, then we get isocontact map from M to N. So this is how one works. So the thing is that you need this extra dimension here. So because N was bigger than M, I could get an extension M tilde Now M could be a closed manifold, but M tilde, when I'm looking at a neighborhood, that is just an open manifold. This is the reason you can apply Gromov's theorem to this special case. Okay. So now the other theorems basically follow from this isocontact immersion theorem. The next step one does from isocontact immersion theorem to Legendrian immersions. So they also satisfy H principle. How does one approach this? Again, suppose you have a contact manifold and so dimension of M is equal to n, and this is 2n plus 1. Suppose we have a formal map which pulls back f star alpha equal to 0. That means the image of capital F is lying inside xi. So this is called the formal Legendrian. So given such a formal Legendrian, the H principle means that you can deform it to a genuine Legendrian immersion. Again, this result follows almost directly from the H principle of isocontact thing. You see that M is embedded in this J1M, which is nothing but T star M cross R. And T star M cross R has a, T star M, as we saw in the morning, this has a canonical symplectic form, which I can denote it by, say, d tau. And then here I can take this to be alpha. Okay. So this is the form that I will be considering on T star M cross R. So this is the Liouville form, and so aim is so J1M together with this. Let me write it. Together with lambda, so this has the same dimension as n now. So on the other side, we have xi to kernel alpha. We have a map from capital F from Tm to the tangent bundle of n. Now, there is a Legendrian neighborhood theorem which says that if you have a Legendrian submanifold, then its neighborhood can be captured by the neighborhood of M inside the jet bundle, first jet bundle of M. Okay. So that will allow you to extend. So the Legendrian neighborhood theorem will allow us to extend. See, M is sitting inside this as a Legendrian submanifold. So will allow us to extend this capital F from Tm to the tangent bundle of n to a isocontact, this is formal isocontact monomorphism, that means injective linear map from F tilde from, I write it J1M, but I don't mean the whole to this, at least on a open neighborhood of M inside the jet bundle. So once I can get this formal isocontact immersion, then I have already have the H principle for isocontact immersion. So I can homotop, so F tilde can be homotoped via formal isocontact maps to a genuine isocontact map. So I will get an isocontact map from some, not the whole of J1M, but on some open subset of J1M into N. So let's write it properly. So this is an open subset which will be containing M. This is an open subset inside J1M, which will contain the zero section. So I have an isocontact map, and if I restrict, so this isocontact map is defined here, F. If I restrict it to capital M, this is already sitting inside this as a Legendrian. Capital M sitting inside this is a Legendrian. I have got an M to N. If I restrict that map to M, I get the Legendrian immersion. So restriction of F to M gives us Legendrian immersion. Okay. So in this result, you need to have this theorem for the extension. Similarly, once you have the Legendrian immersion, then we can prove that the exact Lagrangians also they satisfy H principle. The third result is saying that exact Lagrangians satisfy the H principle. So again we start with a formal Lagrangian. So suppose your N is now even dimensional with some exact symplectic form. And M is an n-dimensional manifold. You want to show that these maps F, which are satisfying this, they are called exact Lagrangian and they satisfy the H principle. So here your formal data would be from equal to 0. So this is the starting point. This is a formal solution is some monomorphism which pulls back d tau to 0. So again the idea would be you use this Legendrian H principle. That means you embed your N to some contact manifold. Okay, so embed N into a contact manifold. So that will define as N tilde, which is N cross R, and the contact form will be given by tau minus dt. So one can show that this is a contact form, and with respect to this, we will be solving the, so let us look at the Legendrian problem. So Legendrian problem at the level of this. What is our goal? First of all, I have a formal Lagrangian immersion. I have to get a formal Legendrian ones. Now if you look at the kernel, so kernel of tau minus dt, this is transverse to the fibers of this. So that it is transverse to the R fibers. So if you take the projection here, that would fall onto the, So if I consider Tn cross R restricted to n, and this is Tn over, then xi will be, if I restrict this projection to xi, then this will fall onto all of Tn. Okay. So here, see, I have a formal Lagrangian immersion. I can extend this thing because of this isomorphism. Here this is an isomorphism, so I can get an inverse map here. Already I have a map going inside. This is my map, capital F, and now I have an isomorphism of xi with Tn. I take the inverse map, so I land inside xi. So I get a monomorphism which maps all of T inside the xi. That means this is a formal Legendrian because xi is a contact structure. So if you have a formal Legendrian, then you again apply the Legendrian H principle and you get a Legendrian map from M to n cross R. And then if you restrict that map to your n, project it map to n, then that will turn out to be a exact Lagrangian. So just to mention, so this composition, the composition gives a formal Legendrian immersion from Tm to T n cross R. You have the xi here. So then let us call this F tilde, then F tilde can be homotoped through formal Legendrians, formal Legendrian immersions to a genuine Legendrian immersion. Let us call this F, small f. So F is a Legendrian immersion from M to n cross R, and if you further project it down to n, then this would be an exact Lagrangian. So pi composed F, which is G, is an exact Lagrangian. So you just need to prove one theorem, which is the isocontact one, and all this follows from there. So finally, I'll just wind up with the isosymplectic thing. So here you have the even dimensional manifolds, and so a smooth immersion, this is called isosymplectic if F pulls back sigma onto omega. Okay. So again, to prove that they satisfy H principle, to prove that they satisfy H principle, first of all, I consider the case okay. Now, as you can see that what does this principle says? Suppose you start with some formal solution F naught which pulls back this sigma fiber-wise to your omega. And you want to homotop this F0 to some J1 or okay, let's say just D of F. F is symplectic, isosymplectic immersion. That means I want F star sigma to be equal to omega. But this has to happen via some homotopy, Ft. So here also you will have to construct Ft, some bundle maps. So on the base you will be having some homotopy Ft of continuous, okay, I can fix Ft. But because this is homotopic to the final map, means the F1 will be your F. Now you require F to be isosymplectic, so in particular F will pull back the class of sigma on class omega. So this is a homotopy, so you have to start with, if you want a solution, then you need to start with an F naught which will satisfy this cohomology condition. This is necessary. Otherwise you cannot for a this capital F naught isosymplectic, because homotopy will preserve the cohomology class. So the extra data that I will need here for F naught will be this condition. But this again a topological condition. So you have a fiber-wise, so F naught satisfies first of all this condition, this is 1, and secondly it has to satisfy this condition. That means the base map has to pull back the cohomology class of sigma onto the cohomology class of omega. These are the two properties of the formal map that we start with. Then the problem again is almost like this. So here I have everything I just replace with. So you have a omega here, you have capital F naught, you have a sigma here. What you know is that this is F naught pulls back sigma onto omega, this is a formal thing, and also you know that this condition is satisfied. Okay. Then as before, I will assume that n is less than n. Then given this formal solution allows us to embed this capital M inside another symplectic manifold, just like before. Earlier it was contact manifold, I was embedding in another contact manifold. So here I will be able to embed, so this is an embedding and this is a symplectic manifold. Okay, so the symplectic manifold also the dimension of M tilde will be same as dimension of N. Okay. So how do I translate this situation into the Lagrangian situation. So now what I want, we want to extend the formal thing. We want to extend f naught to something here. That is also possible, and further we can ensure that this condition is also satisfied. Okay. So starting from this information, I can first of all embed my manifold M into an higher dimensional symplectic manifold where the dimension of M tilde is equal to dimension of N, and then extend this data to this level. Now we are in the again equidimensional thing. So dimension of M tilde is dimension of N. So this will allow us to embed the whole problem in the Lagrangian situation, because I will consider this product manifold. Let us call this P. This is symplectic, this is symplectic. So the product is given the product symplectic form, which I will denote by, say, omega tilde minus sigma. What does that mean? So you have M tilde cross N. There are two projections, pi 1 on M tilde and then pi 2 on N. You have a symplectic form here, you have a symplectic form here. You pull it back, so this is pi 1 star omega tilde minus sigma. Sorry, pi 1 star omega tilde minus pi 2 star sigma. It can be shown that this is a symplectic form. So product of two symplectic manifold is a symplectic manifold by this. So you have a symplectic manifold here, and then if you look at, instead of this, suppose I look at the graph of this map. So consider the graph of f naught tilde. So that will turn out to be a map from TP. And because our map f naught tilde, that was respecting is equal to omega tilde, when I go to the graph map, here I have omega tilde minus sigma tilde. If I put it back, I get simply 0. Okay? Not sigma tilde. I have product manifold. I know that it's just a simple calculation which will give you that if you pull it back by the graph, so you are the situation here. Here you have M tilde omega tilde. Here you have N sigma. You have some graph like this. And if you consider that on the total space omega tilde minus sigma, then graph of f naught, this is formal Lagrangian immersion. So formally, it will pull back this form onto 0. Further, when I look at the base part, then that is graph of f naught tilde, that is the base map. That will pull back to the product form. This is also equal to 0. Because f naught star sigma is equal to omega tilde. That tells you, if you look at the graph map, that means x comma f naught tilde x, that map will pull back this form, this cohomology class, onto 0. So it turns out this graph f naught tilde, this is a map, this is a formal Lagrangian immersion. And this condition tells you that if you restrict this form on this assuming that, okay, this is a smooth thing, I'm not going into further details about it, then this, you have a neighborhood of this where this form will turn out to be exact. Because pullback onto this is 0, you consider a tubular neighborhood, and there this form will turn out to be an exact form. So this condition implies that omega tilde minus sigma is exact on some tubular neighborhood of graph f naught tilde. So we are exactly in the situation in the exact Lagrangian. I don't want to go into further, there are some more technicalities. I have a formal Lagrangian, and if I restrict the codomain to the tubular neighborhood, then there my symplectic form is already exact. So this graph f naught tilde, this map can be homotoped to a genuine exact Lagrangian immersion. So I get an exact Lagrangian immersion here. And again, so this is in the m cross n situation. If I project it further here, I will get an isosymplectic immersion. Of course, I have to say something more that, okay, let's not go into this. So I have a map which is sufficiently close to this original f naught and whose graph is staying in the small arbitrary neighborhood of the graph of f naught. And then you project this map to this, where projection will make sense, because if I want to keep this sufficiently close, and that map will turn out to be a symplectic immersion. See, if you have a symplectic immersion f between equidimensional manifold from m tilde to n, then if you look at the graph map, it goes from m tilde to m tilde cross n. The graph map turns out to be a Lagrangian. Exactly the reverse. If you have a Lagrangian, if you project it down, then it turns out to be a symplectic. So via this exact Lagrangian H principle, I arrive at, so I have this, say, f, and then further project pi 2 composed f. So that will be a symplectic immersion. So though we had started with a general manifold with an arbitrary symplectic form sigma, I can reduce to a situation where this certain neighborhood of the graph will have a exact symplectic form. And the way the argument will go there, that I will always, throughout the deformation or homotopy, I will always remain within that neighborhood. This is called pseudo-dense H principle, because I'm keeping close to the graph f naught. So finally, using the exact Lagrangian H principle, I get back some isosymplectic map between the manifolds m tilde and n. And again, I restrict that isosymplectic manifold to m to get the isosymplectic immersion from m to n. So this is all about the stories about the isosymplectic and isocontact, Legendrian and Lagrangian. But as you see, just one non-trivial result that is needed, that is for the isocontact one, and the rest of the thing just follows easily. So this treatment is given in Eliashbach's Mishachev book. You can see. That mentioned in the first lecture. So I think I stop here.
Questions?
I finished early.
Yeah. So here you have to ensure that the absolute solution is also a graph of solution.
Yes, yes, yes. I can incorporate that condition, yeah.
And the M tilde is similar to the previous construction. It is M cross copy.
Yeah, there you will need some generalization of Moser's theorems. There.
Straight product.
No, this is not the straight product. Here also what I will do is that you have, so the base map will pull back this and then you take the quotient by Tm. So this would be the total space E, which I called M tilde. So M is a zero section here, right? So M is embedded as a zero section here. On certain neighborhood of M, I'll be able to construct a symplectic form using Moser kind of argument,